Hello, my name is Emanuele de Pascale. I am a software development engineer for test at Hedgehog, and today I'm going to give you a brief demonstration of our fabric. So first of all, I'm going to go over the basic abstractions that we use in our fabric model so that you can better follow the steps of the demonstration. Then I'm going to demonstrate a typical GitOps workflow on one of the physical environments in our labs, a spine lift topology with some compute nodes attached to it. I'm going to demonstrate how you can easily deploy new virtual private clouds, or VPCs in short, create and tweak peering policies between them, and also how you can connect your VPCs to external nodes not managed by the Hedgehog fabric. I'm also going to demonstrate how you can monitor your fabric via industry standard observability tools and platforms such as Grafana. A quick note before we start. There is a lot of ground that I will not be able to cover here, but all of these concepts are covered in great detail in our online documentation. There is a link to our website at the end of the deck, in case you are looking for more information. All of the elements in the fabric are represented as Kubernetes custom resource definitions, or CRDs, and as such, they can be modeled via a YAML file. The most basic abstractions we use are switches and servers. Each switch represents a switching element in your fabric, be it one of the many physical white box switches we support, or a virtual switch. Our fabric relies on a normalized resource naming scheme. For this purpose, we provide switch profiles for each of the switch models that we support. These define a standardized naming schemes for port, as well as documenting the switch capabilities such as support speeds, breakout modes, etc. Servers, on the other hand, represent your compute workloads. Their main purpose is to tell the fabric where these compute resources are located in your topology. Servers and switches are connected via connections, which can be of different types, for example, MCLAG, ESLAG, bundled and unbundled. You can also specify external connections, which represent a logical connection between an edge device, which is BGP capable and not directly managed by the fabric itself, and the node of your fabric. The elements we have introduced so far describe the physical topology of your fabric, but now we will look at the building blocks you can use to deploy and fine-tune virtual private clouds, or VPCs, on top of it. Our VPCs are similar to a public cloud VPC like Amazon ones, for example. It provides an isolated private network with support for multiple subnets, each user-defined VLANs and optional DHCP services. A workload can be associated with a subnet in the VPC by means of a VPC attachment object. There's quite a few knobs available to fine-tune connectivity within and across subnets in the VPC. A subnet can be isolated, which means that workloads attached to it are not allowed to communicate with workloads on other subnets in the same VPC. Additionally, it can be restricted, which means that multiple workloads attached to that subnet cannot communicate with each other. Permit lists are available to a variety of settings for specific instances. By default, workloads on different VPCs cannot talk to each other. That's the whole point of having private virtual clouds. But this can be overridden or tweaked using VPC peerings, essentially policies that define which VPCs can talk to each other. They work at a subnet granularity level within a VPC. And as we were mentioning earlier, it is possible to peer with an edge device not controlled by the fabric and import or export routes. Here is the physical topology of the environment in our lab that we are going to use for the demonstration. This was extracted through an automated tool from the wiring diagram, so essentially the YAML files that we use for our fabric, through a tool that was developed by my colleague Pau Capdevila. It is a simple spine lift topology with 2 spines and 4 leaves and 9 compute workloads. The topology allows us to test usual redundancy schemes like MCLAG, SLAG, etc. Additionally, not shown in the diagram, there is an external switch, the DS2000, which we refer to as the default external in our demo. The switches in this environment are all Dells, but we have other environments set up in our lab with different switches from different vendors, including Edgecore, Supermicro, and Celestica. All of the switches are running Broadcom Sonic version 4.4.0. Because our APIs are built on top of Kubernetes CRDs, all of the modern GitHub tools can be used to control our fabric. In this demo, we're going to use Argo CD to make some changes to our deployment. The class is already running. I am SSHing into it. There's also the basic topology already defined in wiring diagrams that are not part of this repo because we don't want to touch them. So we already have some elements for simplicity, two VPCs, demo VPC1 and demo VPC2, and two attachments. Server 1 is attached to VPC1 and server 4 is attached to VPC2. Also, I have already all of the things that I want to create in a commented out YAML file because that's going to make it much faster. So the first thing I'm going to do is create a new VPC, VPC3, with two subnets with different settings, and I'm going to attach server 3 to it. So let's uncomment the related parts and save it. Push it. If you go back to Argo CD, we can see that it has picked up the changes and it's going to apply them to the Kubernetes cluster, which it has just done. So we can now go back to the cluster and go to the control node and double check that indeed the VPC has been created. Another thing that we can do is demonstrate connectivity. So server 1 and server 4 are on two different VPCs, respectively VPC1 and VPC2, and there's no peering between two of them. So if we try to ping between one and another, that should fail. I already set up the ping to save time, and we can double check that it indeed fails. We can change that by creating a VPC peering between these two VPCs. So if we go back to our repo and modify the file again, here we have our peering object. We can see that it peers VPC1 with VPC2, all subnets, no specific constraints. We save it. Push it. Wait until Argo CD picks it up. It should not be applied. You can go back to the cluster. We can double check and the peering has been added. There it is. And then we can try the ping again, and indeed it works as expected. Okay, let's now demonstrate peering to external nodes. So all of these servers are restricted, which means that they cannot reach the internet. If we try, for example, to curl the DNS page of Google at 8.8.8.8, this will fail. In order to demonstrate this, I'm going to use a tool that we developed in-house, HHFab. This is part of our open source platform. I want to show this, even though I will do the curl on the server, because I want to show that through our APIs, you can inspect the fabric and you can realize whether two endpoints, whether they're subnets or servers or IP addresses, they're supposed to be able to communicate with each other or with an external prefix based on the policies that are installed. So right now, as I said, the server 1 is restricted, so if I try to run the curl through this command, the tool is smart enough to understand that it's not supposed to be able to reach 8.8.8.8, and so it tries to run the curl and it fails, but this is expected, so everything is fine. In this way we can run negative tests as well as positive tests. Okay, let's change now this with external peering. So we go back to our repo, again modified file. Here we have our external peering, so let's uncomment it. Here you can specify what kind of prefixes you want to import. In our case, we want to import the default route, so we just specify all zeros, but you could restrict it using prefix lengths or specifying what sort of top level prefix you're going to accept. So let's add it. Push it. Go back to Argo. It's been picked up. And now it's been applied. If you go back to the cluster, we might have to wait a little bit, and the tool is smart enough to know this, because this configuration has to apply to a couple of different switches, and we want to make sure that it's applied. So we're gonna wait until the state is synchronized And the tool realizes that some of the agents don't have the latest generation of config. So it's going to wait a little bit until that is addressed, and automatically it's going to be retrying every 15 seconds by default. There it is. So the external peering has been confirmed. Finally, let's try to send a more significant amount of traffic between two nodes rather than just using pings. So for this we're going to use hyperfs, and again for brevity I'm going to use our internal tool. I'm going to specify that I want 30 seconds of hyperf from server 1 to server 4. And again, the tool is smart enough to know that this should be doable, so it's expected to be able to reach server 4. While this is running, I'm going to use this time to explain our observability platform. So we use Grafana Alloy to push telemetry and logs to an LGTM deployment. We also provide a couple of dashboards that you can obviously extend or customize. These include the state of BGP sessions between nodes of the fabric. You also have traffic counters on interfaces. You can explore logs and the node, each node resource, so CPU and memory usage, etc. So let's go back to our hyperf, and indeed we can see that it worked, that the destination was able to receive the data. So let's try and spot this traffic in our Grafana dashboard. Because this is an MCLAG deployment, we need to figure out which of the spines and leaves were used for this particular traffic. So let's go into the last 15 minutes for brevity, and this is one of the two leaves for MCLAG. I don't see the spike, so let's go to the other one and see if we get luckier. And there it is. Here we can see the traffic going from server 1 to the leaf. And we can probably do the same for the spine, but for brevity I'm going to skip that step. This is where our demo ends. I've shown you how you can manage your fabric infrastructure as code using GitOps workflow. I've demonstrated a subset of the many knobs available to control connectivity of your workloads, both within your fabric and towards the external world. And I've shown you how you can monitor your fabric using industry standard platforms. If you're curious to learn more about our solution, please head to our website, where you can find much more detailed documentation of all our APIs. We also encourage you to try this for yourself using our virtual hub environment.